In the previous video where I was adding acid and base to Alka-Seltzer, the color did not change very much. And the reason for that is because of what we're about to talk about in regards to buffers. Alka-Seltzer contains the weak acid citric acid, which will be represented by HA because I don't feel like writing out the big old long formula here. The dissociation equilibrium is just like we've been talking about. It's the acid is breaking apart into H plus and A minus. Since HA is a proton what does it do? It's an acid. Acids are proton donors. A minus will then be a proton acceptor, right? As a result of these two things, we understand what's going on inside that acid. The acid itself is a proton donor. Its conjugate base, again, A minus is the conjugate base of HA. Since it's a conjugate base, it will be a proton acceptor. So using Le Chatelier's principle, what's going to happen with each of these things? If I add H+, obviously the concentration of the hydrogen is going to increase. If that increases, if the amount of hydrogen that I have goes up, then the amount of A minus is going to have to go down. These two things are going to react together to make these things go away, to make more of the HA. And if I add OH, what is the OH going to do? The OH is going to cause the H plus to go down. If there's less H plus, then the HA is also going to go down in order to produce the A minus, to keep our K constant. In Alka-Seltzer, the lack of color change is due to the fact that any hydrogen ions, when I added the H plus, the hydrochloric acid, they're all used up. And the removed H plus ions are almost all replaced, no matter what I was doing. If I was adding acid, then they were going to be used up by reacting with the A minus. If I added OH, the H pluses are being neutralized, but new of them are being replaced because as the reaction takes place, the HA will then shift to the right. As I remove H plus, it's going to shift my reaction to the right, and as it shifts to the right, I'm going to make more of this stuff to replace what I removed. Same thing here. If I add more of this, it's going to shift to the left, and it's going to make more of that. These are going to go down. So what we can say is that the added H plus ions are almost all absorbed. What are they being absorbed by? They're being absorbed by the A minus. And the H plus ions, which are being removed by the OH, are almost all replaced by the HA. Okay. The solution itself, the Alka-Seltzer solution, contains large number of both donors and acceptors, the conjugate base of the weak acid. Just like this. There's lots and lots and lots of this, and lots and lots and lots of this already in the container. So solutions with large concentrations of acids, large concentrations of bases that are not neutralizing each other, because aren't those what do we have here? This is an acid, this is a base, but they're not neutralizing one another. So those two things are thus called buffers. And I'm trying to write with a mouse instead of on the board. So these buffers are what we're going to be talking about here. There's a lot more to talk about with these things called buffers, but I'm not going to do it on this portion here with all of the stuff here. I will start a new page, and I will pick up with that in just no need to say in a little while because it's just a pause. All right, so here's the deal. A buffer. The best buffers that we have are able to react with both hydrogen ions, the acids, and hydroxides, and it keeps them relatively the same pH. Now, of course, as it's changing the quantity of H plus and OH minus, it is going to change the pH. We will actually want to have equal quantities of both the H plus and the A minus in our system. Or if it's a base, a weak base, and it's conjugate acid. We want to try to have as much of both of them as we can in the system, and lots of them. The more we can have, the better buffering capacity that substance will have. I will be able to add acid and base to it, and the pH won't change very much. So here's the whole point of why we're doing this. What will happen if I have a Ka value, which we know for a specific acid, Ka is the concentration of the ions of the hydronium times the conjugate base divided by HA. That's the products over the reactants. What will happen, mathematically speaking, if the A minus is equal to the HA. So like we said, if we have equal quantities of both of these things, what's going to happen? The A minus and the HA are going to cancel, and thus Ka is going to be equal to the concentration of the H plus. And if you remember, we said once upon a time that we could have this thing called P. So if I were to take the pKa, wouldn't that be the same thing as taking the pH? And the answer is yes, they are the same. So what we're going to do when we're looking for buffers is we're going to look at what's called the pKa value. The pKa is going to tell us the approximate pH that we can make from a buffer made of those substances. I'll show you a couple examples. So formic acid is a weak acid that has a Ka value of 1.8 times 10 to the negative fourth. We can look at the dissociation of formic acid from HFO, being FO being the formate ion. So when it goes into water, we get the acid reaction. So we have an acid, the conjugate acid is here, and the conjugate base is here. So what would happen then if I were to take sodium formate? So this salt, sodium formate, is going to be able to be dissociated in solution. As it dissociates, the sodium ions are going to be spectators. Why? Because they're the conjugate of strong. And the formate ion is the conjugate of this weak. So this thing is going to act like a base. So when I put both of these together, let's say that I took 5 molar formic acid, so 5 molar HFO, and 5 molar sodium formate. What do I have in my container? Well, I'm going to have two separate things. I'm going to have this formate ion, I'm going to have this stuff here, and I'm also going to be making, sorry, that's the formic acid, and I'm also going to have, if I can find, I'm going to have the formate ion. Oh, I made a little smiley face. So, if we were to rewrite this again as a separate reaction, separate way of looking at this, of what's going to take place, here's what we're going to have. In my solution, come on, nope, that's not what I wanted. I want HFO and water to form the ion of the acid and the formate. So now, what is my initial concentration? I had 5 molar formic acid, and I had 5 molar formate. Okay, so now if both of those are in my container initially, what's going to happen is we change. Now again, we're already talking about this solution is at equilibrium. I used 5 molar of this and 5 molar of this. So this would be like 5 moles of the hydrogen formate in solution with 5 moles of, in 1 liter of solution, 5 moles of the sodium formate. Where are the sodium ions? Sodium ions are spectators, right? So they're not even here at all. We can ignore them. So we can always ignore the spectators. So now if I have this situation, I have 5 molar formic acid and 5 molar sodium formate. Anything that I add, if I add a little bit of H plus, so if I were to change by adding some of this, what's going to happen? Well, these two things are going to react, and it's going to cause the reaction to shift towards the products. And we're going to get a little bit less of the formate ion. This is going to go down, right? And then this is going to go up. That way. All right? When it comes back to equilibrium, we're not looking at equilibrium. We're looking at a neutralization that's taking place. If I put these hydrogen ions in, it's going to neutralize some of these pieces. So the 5 molar is going to go away, and we're going to say it's something like 4.9. Let's just say I neutralize 0.1. If I neutralize 0.1 of these by adding more H+, then I'm going to make 0.1 of these. So I get 5.1. And now if we go back to our Ka, this is a Ka expression, acid, right? This was the concentration of H3O times the concentration of FO minus, all divided by the concentration of HFO. So if that's what I have, now I know the concentrations of these things. So what do I have? I know the Ka, right? The Ka was what was given to us up here at the beginning. Oh, I never gave it to you. It was on the previous page, wasn't it? There it is. Ka is 1.8 times 10 to the negative fourth. So if Ka equals 1.8 times 10 to the negative fourth, then we're still going to have the same thing here. I'm going to have 1.8 times 10 to the negative fourth equals H plus times 4.9 divided by 5.1. Right? Those are those concentrations. And so now as I do this math, it becomes relatively easy. It's almost the same, but it's a little bit different. Let me crack out my calculator here and do this problem. So I'm going to take 4.9 divided by 5.1. I get 0.961. I'm going to ignore the phone for a minute. And I need to divide both sides by that. So I'm going to take 1.8 times 10 to the negative fourth divided by that answer. And I get 1.87 times 10 to the negative fourth. Notice the difference isn't much, right? So that's now our concentration of H. If I wanted to find the pH, I take the negative log of this, and that value is now 3.73. Previously, if I had taken the negative log of this, the negative log of 1.8 times 10 to the negative fourth, it was 3.74. Interesting. I added a little bit of H plus. Remember, I added this to our solution. When I added this stuff to my solution, what happened to the pH? It should go down just a little bit, but you won't be able to see the difference in 0.01 pH. I mean, that is so negligible. So we added a little bit of the hydrogen, and the pH came down. So what we're actually seeing is that if I want to know what I should use as a buffer, the best buffers are whatever you have a weak acid at that Ka. So we just said that last one, 1.8 times 10 to the negative fourth. This best buffer is going to be a pH of around 3.74. If I were to use something like acetic acid, 1.8 times 10 to the negative fifth. So this one is just a little bit different. It's 4.74. If I were to use a different Ka value, let's see if I can find one because I wasn't prepared for this portion. I don't have one right in front of me. Benzoic acid is 6.3 times 10 to the negative fifth. So that's a pH of 4.20. This would be the buffer. These are the Ka values over here. The buffer at equal quantities will be this value. I would have equal quantity of both the acid and the base. Again, one other one, if we were to look at something that has a Ka such as 5.6 times 10 to the negative 10th, if I were to use that as a buffer, it's going to make a pH of 5.6 times 10 to the negative 10th, pH of 9.25. All right, we can then adjust these pHs if we were to adjust the concentration of the anion to the actual acid. So this is called the Henderson-Hasselbalch equation. pKa equals the pH plus the log of the concentration of the A minus divided by the concentration of the HA. It works the same way for bases. If I want the pKb, it's going to be the pOH plus the log of BH plus divided by the base. Hopefully this is starting to make a little bit of sense. I'm going to stop this lecture for this part here, and I'll pick up with another one doing some more stuff regarding titrations in just a few minutes.